All right, we're going to try to come in and do this with the video again, see if that works. What I want to do first is I want to kind of talk about the behavior of the polynomials as they cross with multiplicity 1, 2, or 3, and what I really want you to notice. And so what I really want you to notice is kind of when you're looking at this, see right here where it crosses, this is a single, and a single. And the same thing over here is a single, and then here, here, and here. That if you were looking at those, hopefully what you recognize is that what it does is it kind of crosses the sign changes of the function because it goes from either positive to negative, negative to positive, but it crosses like a line. And a line has a degree of 1. And so single multiplicity crosses like a line. So that's one thing to look at. Then look over here where it had a double multiplicity, a double zero or multiplicity of 2. Do you see how if I were to zoom in right there that would look kind of like a parabola? So it kind of acts like the behavior is very similar to a quadratic, where a factor occurs twice. You see my dog here. So when you're looking at that, that's the behavior when you have a multiplicity of 2 or an even multiplicity. It's going to have that idea where it's a vertex, where it's tangent to the x-axis, and the sign does not change. It's the same sign on either side of the 0. The function h of x is negative, and then hits the 0 and touches the x-axis, and then it is negative again. So the sign does not change. And then if you take a look over here at our POI, where it's crossing, where it looks like a cubic, remember the looks like a cubic, that looks like a parabola, the singles look like lines, and then the cubics, or the crossing with the triple zero multiplicity of 3 looks like a cubic. And so hopefully that gives you an idea that when we're looking at the graph, we can actually determine kind of the multiplicity simply by looking at the graph. So if we scroll down to this section of the graph, why don't you guys answer 2, 3, and 4 and then come back? Okay, summarizing what we just talked about then, when we take a look at this, the important thing is that whenever the multiplicity is odd, then the function is going to cross the x-axis. So notice that it crosses here and crosses down here at the bottom. So that's happening each time the multiplicity is odd. So every time the multiplicity is odd, in addition to crossing, there is going to be a sign change at the 0. Now, it's how it crosses that's kind of telling us a little bit more information about the multiplicity. Now, when it crosses like a line, just straight across and crosses, then we would know that most likely the multiplicity is going to be 1. And then if you're looking at it and it looks like it crosses like a cubic where you have a kind of flattened little point of inflection going up like that, then that is going to be an indication that you have a multiplicity of at least 3. Now, I'm going to say odd, like it could be 5. It's one of those things that we're just trying to do like the minimum amount, or 5 or 7, etc. Because technically we don't know. A fifth degree, like y equals x to the fifth, and y equals x cubed, they look very similar to each other with that point of inflection. So we don't really know simply by looking at the graph what the actual multiplicity is, but we definitely know it's odd. And because we have that leveling off and then continuing up, that's going to give us the idea that the power on, or the multiplicity or the power on that factor is going to be odd and bigger than 1. It's either going to be 3, 5, 7, or so on. Definitely odd and going up. But if it crosses like a line, the multiplicity is definitely going to be 1. And then the behavior of the graph when we are looking at it in terms of a double zero, those will have a vertex. It's going to be tangent to the x-axis. The 0 is going to be a vertex. It's going to bounce. And so the sign will not change in that scenario that you have. All right, so let's pause that. Let's scroll down and see what the next section is. All right, so for the next section coming in, what we're going to do is we're going to combine together what we did in the previous section with synthetic division in finding the zeros and finding their multiplicity using synthetic division, as well as taking a look at this. So when I look at this factor x plus 1, that means that our root, when we take a look at it, is going to be -1. And so what they've asked us in the instructions here is to identify the 0, which I did, and then we're going to use synthetic division to help determine how many times it goes into it. So remember synthetic division, we're going to do our -1, grab your coefficients, 1, 2, -1, -2. We're going to run synthetic really quick, so drop your 1, multiply, 1, multiply, -2, multiply, 2, and that gives us a 0. And so now looking at that point with this one, if you can get yourself down to a quadratic, I typically don't continue with the synthetic division. I would simply then write it in factored form. So f of x is going to be x plus 1, and then x squared plus x minus 2. And then I would go ahead and I would finish out the factoring on that. So we would do an x and an x. We need a 2 and a 1, and that's got to be positive, and that has to be negative. And then from there, I definitely know that my multiplicity, because I only have the factor to each of these is to the first power, so the multiplicity is 1. And notice that, kind of what we said before was it crosses like a line, okay? It has a single multiplicity. The sign changes. If I were to do a sign chart kind of corresponding to this graph for f of x, your critical points would be at -2, -1, and 1. Those are the zeros. And because we're below, above, below, and above. And so what you see is that the sign changes on either side of -2, changes on either side of -1, and changes on either side of 0. So all of these are going to be odd multiplicity just based on the sign chart because they change signs. And then because when you look at the graph, you see that it looks like a line each time that it crosses here, here, and here. And that also in my synthetic division, I can see that I have a power of 1, 1, and 1. And so they are going to be very much a single multiplicity graph. So it crosses like a line. It changes sign. Therefore, my multiplicity is going to be equal to 1 for that. All right, why don't you guys, I'm going to take a pause here and figure out why my dog is barking. And you guys go ahead and complete the h of x and also the p of x and see kind of how that works. And I will tell you that in p of x, when you're doing your factor of 1, because we've already talked about this, that this obviously is not going to, sorry, let me scroll down here for that one. So this obviously does not cross like a line, it crosses like a cubic. So we know that this has odd multiplicity greater than 1. So when you do your synthetic division, make sure down here that you go ahead and you divide that 1 in more than one time. So -1, 1, 3, -5, 2. And so you're going to go ahead and you're going to do the division and just, you should get a 0 there, and then divide the 1 in again and continue the process. All right, so why don't you guys go ahead and do that and kind of get to right there and stop there, and then we will come back and discuss. All right, so coming back in, taking a look at this, kind of finalizing and summarizing this portion of the notes, that when we look at it in terms of crossing like a line, I will say I did add in here for you guys that when you look at it, the crossing like a line looks like never proves anything in math. So just make sure that if you want to prove that it actually does have a single multiplicity, you really have to show that it only divides into the polynomial once. And so I did want to kind of put that out there as something to look at. All right, let's take a look at what you should have gotten for the next one. So when we look at that one, again, our root is 1, and we went ahead and did our synthetic division, and notice that I was able to do the synthetic division twice, that I ended up with a 0 in the first division and in the second division there. So it went into it twice. And so what we know is that factor goes 2 times. Now I went ahead and I wrote it down here at the bottom. I do want to kind of highlight one thing for you here. Notice that this factor, the factor that was remaining, the 2x plus 3, like one of the things that a lot of them, when I was initially talking about like a lot of these different functions that we were looking at, the idea was that like in completely factored form, this would be perfectly fine. Sometimes people like to write it in a factored form where they have x minus 1 squared, then you have x minus our 3 halves. And notice that what I'm missing there is that like that coefficient, that's the 2 that's in front of that. It's kind of like they factored the 2 out. And so this right here, whenever I talk about a scaling factor or a scalar, that a lot of times when you are creating that formula, we kind of prefer it sometimes written in that format. So that way we have our nice linear factors as well as the scalar in front. So just know they're just different forms of the same line, just different ways of looking at it. Just be familiar with that. All right, and then down here describing it, I did went ahead and said, well, the behavior of the graph at the 1, it's tangent to the x-axis at 0. The 0 is a vertex. It acts like a parabola. I didn't say that, so let's add that in. The 0 is a vertex like a parabola. And again, the idea here is that once I see that it looks like a parabola, what I know, and again, there's no sign change, when I'm looking at that, I know that that has even multiplicity, 2, 4, 6, etc., kind of as we're going through that. Now, in this problem, I know it can't be 4 or 6 because the degree of the polynomial is only 3. So you can't be any higher than that when we're looking at it. But if this had been an 8th degree or, sorry, 7th degree polynomial, then I clearly, when it bounces like that, it could be an even multiplicity and have 4 times. So again, the idea is that when you are trying to actually prove the multiplicity of it, you're really checking to see how many times it divides into it, and it only divides into it twice, hence it has a multiplicity of 2. All right, and then our last one down here, taking a look at that one, same kind of idea. We had our root, which was 1, and taking a look at it, divide it out. I managed to divide it through 3 different times. So I got my 0 remainder in 3 different cases. Again, I wrote it in the nice factored form, taking what was left, the negative x minus 2, and putting it in its factored form. Again, I didn't really like that the factor right here, the negative x minus 2, I went ahead and factored a negative out of that to put it in that, again, that nice form. So again, my scalar, my a in this case would be -1 in terms of that problem, just to show you a different form of looking at it. Now again, we looked at it, it crosses like a cubic. We had a sign change. Did I say that? Changes concavity, the 0 is a point of POI, sign changes at the 0. So again, here's that sign change. What we know is that we have odd multiplicity. And if it had looked like a line, it would have been odd multiplicity of 1. But because it looks like a cubic, the multiplicity has to be 3, 5, or 7. But again, we can take out the 5 and 7 because it's a 4th degree polynomial, so the degree kind of caps it on that one. But again, the only way to prove it is to actually do the division and see how many times that factor divides into your polynomial. All right, I'm going to stop this video at this point, and we're going to come in and do the next section in another video. Sorry, there's a lot of videos for this, but this was a very rich set of notes. It had a lot of things for me to talk about.